right, ladies and gentlemen, so we're going to be doing our flip lesson here, and I promised you to keep it brief, so I will. All right, what you're looking at right here is a potential energy diagram. Okay, this is just one type. We will see a couple of variations on this, and we don't have any numbers on the side. We would normally have a ranking of kilojoules on this side for energy, and you might see time on the x-axis, and so that could be a variation. Now, when we have different values on the graph, we will be able to drag across and see what energy that point on the graph is correlating to. But right now, I just want you to get to know and be familiar with the parts of the graph. So we are going to run through each of the vocabulary terms that are down here, and we are going to label our graph with them on there. I need you to be confident with these vocabulary terms so that we can continue to talk about them tomorrow and Friday. All right, so we're going to start with our first one. So we're at the potential energy of our reactants, and this is the amount of energy that a system starts with. It's the amount of energy that is present at the beginning. So if we take a look at our graph, we can see that right here, this point right here, that's going to be the potential energy of our products. It's the potential energy of the point at which we're starting. And if we were to take this and drag it across and get a value, we could really do that and get a kilojoules value for the potential energy that we're beginning with. So let's label our graph with that. All right, so you can see I've labeled it as the potential energy of the reactants, and actually it is A, so the value that is A, this entire energy level right there. All right, so let's take a look at our next one. We have the potential energy of the products, so very similar to the potential energy of the reactants. This is going to be the amount of energy that the system ends with. So because of that, we are going to take a look on up here to the end of our graph, and we're going to be dealing with this amount of energy, which starts at the bottom and goes right to here, and we can get that kilojoules value from a labeled graph. All right, so go ahead and make sure that you have that labeled for me, please. All right, now we're going to head down to our next one. So we're at the activated complex. And now I've written here for you that the activated complex is actually the peak of our graph. And what we need to understand is the activated complex is the highest energy point of the reaction. This is where a full rearrangement of the reactants occurs. So where we take our reactants and we break all the bonds and we start to form our products. And this must happen in order for our reaction to be successful. Now, because we know it's the peak, we can very easily go right to our peak here, and we can see that this point, the point right here from the peak down to the bottom, this whole thing represented by C is going to be our activated complex. Okay, so we're getting to the end. So the activated complex is our highest point, and we must get over that hump in order for our reaction to proceed. So let's get over to the next ones. We have the activation energy. We've actually already talked about this one. The activated energy is the energy needed to get a reaction to happen. It's the energy needed for us to get over that hump, to occur. Okay? It's the energy that we need to get over that highest point in our peak. So if I am coming from my products, it's the energy that I need, for my reactants, it's the energy to get from here to over my peak. And so in this case, it's going to be illustrated by this distance. So from my reactants to my peak. And so what's actually B labeled on your graph is going to be our activation energy for the forward reaction. All right, so that you can see I have it labeled here, and make sure that you realize that it's this distance from our reactants up to our point where our peak is. So it's really B. All right, so now you'll notice if we go down, there are a couple of other things under activation energy. We have the activation energy of the forward reaction, but we also have the activation energy of the reverse reaction. Now what I've labeled up here as the activation energy of the forward reaction, that's the activation energy of the reaction proceeding from left to right, starting over here with our reactants and over here with our products. And that's the way we normally visualize a reaction. But we can also move this way. And if I move from right to left, then that's something called the reverse reaction. And when I have a reverse reaction, that means that I'm going to start here and I'm going to go up to my activated complex. And so I actually have a different activation energy. I have an activation energy that starts down here and needs to get up here. So this distance from point, what's labeled a D, going up to my activated complex, that's going to be my activation energy of the reverse reaction. So from here all the way up to here. All right, now please make sure you have that labeled. And as we go down, we only have one more vocabulary word to go over. And that vocabulary word is the heat of the reaction, and that is going to be our delta H. And this is a formula we've already seen, but we want to see what that looks like on our graph. So delta H, meaning it is the difference in potential energy levels between our products and our reactants. All right, do make sure you have that definition down, and we're going to head up to the top and see what it looks like. All right, so, whoa, that arrow is still moving around. Okay, so if I take a look here and I want to see where my potential energy of the products would be in a forward reaction, that's here. And I see the potential energy of my reactants, that's here. So the difference between them will be the difference between this point and this point, which actually happens to be this dotted line here and here, and the difference between them. So right there, that is going to be my delta H. So if I subtract those two values, I will get the difference between the two of them. All right? And so we see that this is a very important part of our understanding of a potential energy diagram, and it's probably one of the biggest things you are going to have to pick out. So please remember that it's your products minus your reactants, and you would have numerical values for the product and the reactants to get a numerical value for your delta H. All right, thank you for watching. And I know I went over my 5-minute time limit, but I don't think I did too badly. All right, so thank you very much for watching, and I'll see you tomorrow.